Welcome, everyone, and thank you for joining us today. And welcome to our 12th and final webinar of 2024 and our year-long series of webinars celebrating 20 years of the Data Distribution Service. My name is Laura Clark. I'm VP of Communications for the DDS Foundation. In case you haven't heard of us, the DDS Foundation is a nonprofit community of interest for users and developers of the family of Data Distribution Service standards. Our mission is to drive the adoption, interoperability, and success of DDS. If you'd like to get involved with the DDS Foundation or have ideas of something you'd like to see in future webinars, we'd love your input. Visit our website, dds-foundation.org, and click on the Get Involved tab. It's my pleasure to welcome David. David DeBari is the technical team leader for the ExxonMobil Open Process Automation, OPA program, and one of the original members of the OPA program team formed in 2012. He has provided technical leadership for the foundational ideation, the proof of concept, pilot unit prototype project, and the test bed facility, and is currently guiding the team in the OPA Lighthouse Project R&D activities for the ExxonMobil program. And now I'll turn it over to David.
Thank you. So again, my name is David DeBari. I work for ExxonMobil. I'm going to talk to you today about how we believe we can leverage DDS for enhancing our fault tolerance. So today, I'm going to give you a little bit of an introduction. We're going to talk about some of the specific problem that we were looking to solve and how we realized that DDS was the answer for us. I'm going to talk to you a little bit about interchangeability, which is related to using the DDS, and it adds some features and things to the system that would allow us to achieve this elevated reliability. And then, of course, we're going to talk about the configurable reliability and fault tolerance, which is the purpose for the using DDS. So I'll start with myself. I am a jack of all trades process control engineer. So I'm in the business of using computers and electronics to operate manufacturing systems. Specifically, I work for a company that has chemical facilities, refineries, and other kinds of facilities, whether it be pumping stations, transfer stations, even the systems that fill the trucks that deliver the gasoline to the service stations. But a process control engineer is what I am. I am not an IT person per se. I have a lot of IT skills, and but I also know a lot about things like transmitters, valves, pumps, motors, those things. I am an end user that is in need of some technology. I live in a world that the technology has seemed to have stalled, and what we realized is we need to get back to putting technology back into our systems. Many of our automation systems and process control are stuck in the 90s, so the technologies we're using are getting quite old. Another thing I want to tell you is I'm an innovator, and I'll tell you my definition of innovation. Being an innovator, you have to be comfortable with ambiguity. The answer most days is I don't know yet. That you have to be at ease with uncertainty. You don't know the answers. That's why we're doing the innovation, the R&D, the kind of activities like that. We have to embrace manageable risk. There is risk of failure. And in the last point, you'll notice that if you're not failing, you're actually probably not doing your innovation correctly. I lead a team of subject matter experts. I'm very fortunate. I have a great bunch of people. And but what I tell them is we're not here to test it. We're here to torture it. I want to see if we can break it. Now, when I say break it, I mean find it where it faults and where it fails, and then you know something. But I don't encourage them to burn the building down or anything like that. But that's sort of what my take is, and that's who I am. All right. So obviously, you all are attending this, and you know a little bit about DDS, and of course, the DDS Foundation supports this. And, here's some of the information about who they are and what they're doing, promoting adoption and helping people understand and learn more about it and advance the cause. And that's this piece. I'll just keep going. All right. So let's talk about configurable fault tolerance, and that's the I think the original title for when I myself and some of my peers put this together several years ago. But the title, the original title, is really what we're trying to do. All right. So, what is the problem that we were trying to solve? Now, obviously, I told you we're in the process control world, so I'm trying to solve a process control problem. But a lot of these problems are very similar, whether you're solving a business problem or a process control problem or any other sort of issue. Um, but for us, it was about edge computing reliability. We have computers that we use, we call them controllers, and they sit in the process and they talk to I/O, which are just electrical peripherals for inputs and outputs. They are very highly coupled software to hardware devices. If you buy one, you get the software. If you want the software, you have to buy the device. They come in two forms generally. One is called a programmable logic controller, which is generally a very simple processor. It runs very fast. It was generally designed in the discrete world, so the people who bottle beer and can soup and move boxes down conveyor belts, the PLC was their primary tool for automation when it came to computers. Distributed control systems are another variation of this model, and that is generally used more by people who do things that like a chemical plant, um, reactor vessels, the pharmaceutical folks at DCS. And there's some subtle differences here, but basically it's the same thing. Computers making calculations, writing to I/O, reading sensors, temperatures, levels, pressures, that kind of thing, and calculating what to do with the motors, pumps, valves. And that's sort of where we get to. Now, recently, obviously, IIoT, so the industrial Internet of Things has come about. And the thing we're realizing is we really need open standards-based architectures. There's a lot of proprietariness to our world in the legacy systems, and that's a problem. We need to get higher performance computing. We need to have state-of-the-art security, and we need more flexibility in what we're doing at the edge. And so when we talk about edge computing, we don't have much of that, and we want to bring more of that. And then that means we're going to need communications, and we're going to need capability, and that's why we're having this discussion today. Basically, for edge compute clusters, we had several quality attributes we were looking at. Hardware interchangeability is one of them. Configurable reliability is the second one. We have two flavors of interoperability and portability. And so we want to be able to move software to different platforms. And we also want to take our configurations from the software and move it between different software applications. So those are the two forms of portability that we felt were very important. And today we're pretty much going to focus on the facets of hardware interchangeability and configurable reliability. So I'm going to tell you a little bit about hardware interchangeability just to give you a foundation on where the configurable reliability comes in. All right. So here we are with 125 years of Moore's Law. And think about it, Moore, he deduced this back in the 60s and 70s, but it does go back beyond the time that he came up with this idea. And if you look at this is sort of the evolution of our technology. And so in the 70s, we started getting, I'll call it the computers that we're used to today, the integrated circuit version. I'm not old enough to have seen the big rooms of vacuum tubes, but I've seen the pictures. As you move through time, we start getting, and you'll remember some of these. Some people will remember them. Some of them will have heard about them. And it's really weird to think about, the power book is back in the early 2000s, nearly 20 years ago. So here's the thing: in the automation world, a lot of our computers are state of the art 1980 something. So you can imagine where we're at in terms of power and capability. So what is the result of that? Well, we have all this lost opportunity. Um, we're not using the latest technology and the latest capabilities, and these are affecting us. They are affecting our ability to be successful and bring benefit to our companies and solve the problems we've been given. Um, Obviously, in today's world, cybersecurity, top of the list. Um, Back in the 90s and 80s, cybersecurity was not the same issue. And so we're dealing with technologies that were put together and perfected back in the 80s and the 90s. And cybersecurity generally isn't one of the top features they have. Obviously, today's world, we're doing advanced process control, advanced mathematics, and that extends all the way into the latest, the buzzwords of AI and ML and digital twins and all that stuff. Real-time optimization has been part of our world for a while. We generally have to bolt it on because the equipment won't do it. Some other things, monitoring and detection, things like high-speed logging. Many of these computers are pretty slow. Um, we buy processors today that still have processors that run in the megahertz range and memory that we have vendors will tell us there's a lot of user memory. And when they say that, they're talking about 60 megabytes. And so this is not a very good thing. Obviously, today we start thinking about software-based soft sensors and other things, and that's the world we need to be in today. It is 2024, soon to be 2025. And so this is sort of the state of the world. So talking about interchangeability, interchangeability is the ability to replace the components or the part of the equipment. And so when you think about it, interchangeability is the physical variation of interoperability from a software sense. So the idea is, can you swap? I mean, we live with this every day. You can trade out a mouse, you can trade out a keyboard, you can trade out a C-size battery, and these are all methods for interchangeability. You don't lose function. You trade it out with something else, a different brand, a different capability maybe, but you get that same functionality. So today, our for edge hardware, we want interchangeability because we want to eliminate the cost of switching. I don't need to redesign everything. I want to have the same features when I put a new device in. I want to have choice. I want to have better performance. I want to improve my security. And given Moore's law, it all ought to come at a lower cost. So that's where the interchangeability fits in. I need a hardware platform to run my software and to support my communications for the solution. So at ExxonMobil and with a bunch of other people, we've been working on how to move to open standards. And we formed something called the Open Process Automation Forum in late 2016. And part of that is a lot of software interoperability and harmonization and using open standards. But another piece of this is about the interchangeability of hardware. If we have something fail or you have electrical problem, lightning strike, whatever, you have to trade it out. They do die. And the challenge you get is they're not interchangeable. They're not very easily replaced. So you either have to get the same make and model, and you might have to wait. And these are the issues. We said, well, in a lot of the rest of the world, if you lose a monitor, you can get one. If you lose a mouse, you can get one. If you decide to change your TV, you plug it into your DVR or your internet system, and it works just great. Well, why don't we have that? Why is it not interchangeable? So we started this process with Georgia Tech Research Institute to identify some standards, and we then started working with the wonderful folks at PickMG. And if you've ever traded a card in your PC, PCMCIA, these are the people that do that standard, plus many others. And so we went to them and said, hey, you guys can help us, because a lot of the hardware interchangeability has to do with common connector. It's the USB, USB-C, HDMI. Pick your connector. When you want physical interchangeability, you're going to need a common connector. And so what we've done is we've worked with PICMG to develop something we call InterEdge. And so the InterEdge standard has been worked on, and we did release release 1 in 2024. We're actually working on version 1.1 now with a few additional enhancements to that. So this is sort of the interchangeability story. And here's a list of some of the companies that are associated with this InterEdge activity with the PICMG organization. A number of these are people who make things and use or manufacture the connectors, and would then put the products together, and we as end users would end up buying them. All right, so the InterEdge specification is mostly about size and power and weight and thermal and what's the connector look like and which pin does what kind of stuff. There's some stuff on how big it can be and what size of box it's got to fit in, what pin 20 and 21 do. These are things, voltage and communication signals and grounds and that sort of thing. All right, so enough about the interchangeability. Let's talk about where DDS comes in. So this is configurable reliability and fault tolerance. All right, so I'm going to start with a little bit about reliability and availability. And many people have heard about the bathtub curve, and what is it really? Well, if you take infant mortality, where things die initially, and you made it with end of life wear out, that's the ends of your bathtub, and the bottom of your bathtub is constant random failure models. There is a little math here in a minute. We're not going to spend too much time because I don't think that's the purpose of this discussion. But the math does follow the reliability and failure calculations that people do to figure, when you hear mean time to failure and availability, it's been calculated, and this is how they do it. So if you ever heard about the bathtub curve, things die early, or they die somewhere along the way, or at the very end of life, they definitely, it picks back up, and that forms the bathtub. So the reliability is the probability the component is going to be available over a specific, that it'll function over a specific period of time. And we have a term which is reliability, sub I over time. And of course, that means there's some math. In the reliability world, they like to use lambda. And so they solve for lambda in this way. And so you see these R dots, and the R dots is a derivative, and we won't go too far into this. But basically, you get to formulas where you can figure out the reliability of a component over time. And so then what we can do is we say, all right, over time, brand new, it should be great. So the probability it'll function at time 0, it's 100. You plug it in, it works, everything's good. And then if you have a certain curve like this, and this is a picked lambda, if you will, the lambdas form these lines, and if you follow it, well, about 3 years down the road, it's about a 94% chance that it's going to function. And you can see it at 5 years, you're down to 90. And this is a particular curve, and we'll get to why this is important in a second. So the reliability is a set of, so now we want to create a system. And a system is a set of components. And what we believe is a parallel set of components will work very well. So we have our reliability, our probability of success, and the probability of failure is just 1 minus the probability of success. So this is just following along the reliability as it goes down. And so here we have a system of parallel devices. And for simplicity, we'll just call them hardware only, use the same devices so we don't get any sort of variations there. And then we'll consider them independent nodes. They are not reliant on each other to exist. So R1, R2, all the way to Rn, individual devices in parallel here. Only one of them has to work for the system to function. So you take an input, as long as it can pass through one of these devices and get to the output, it's functioning. All right, so the reliability of the system is a function of the individual components. Again, more math, I'm not going to go too far in this. We do some rearranging, and you can figure out that the reliability of a device, if you have a certain system reliability, can be calculated. And then we solve for the lambda, and of course we end up with a really fancy equation for the device based on the system reliability. Okay, so we've done all the math. Why? Well, we want reliability curves. So when you start talking about equipment, there are people call them, 3 nines, 4 nines, 5 nines, or 6, 7, 8, 10 nines, whatever you want. And so what this reliability means is 99.999% available. So 5 nines, that yellow line, is basically 5 minutes of downtime a year. 6 nines is 30 seconds a year. 7 nines is like 3 seconds. You can see what's happening there. The idea, you're running a process. You're flying a plane. You're doing something important that needs to stay online. You want high availability. So with these curves, you can tell, all right, if I have so many nodes in my parallel system, what's the individual reliability that will give me this 4 nines, 5 nines, 6 nines, whatever we're shooting for. So in our traditional control systems, we generally have 2 nodes. They're redundant. As you can see, the reliability is about a 99.6 individual of each device, and the mean time between failure is 316 years. It's pretty cool, although I don't know there are any computers that are 316 years old yet. But if we want to stay on this curve, but we want to use more nodes, we see something very interesting happen. If I go to 4 nodes, the cluster, and focus was the name of something before, InterEdge. Sorry, I reused a chart, but I couldn't change the label. But with 4 nodes, I only need a 94% available device. And what I will tell you is you cannot buy a Raspberry Pi that bad. So, we're getting out into devices that are a capability requirement that is way below what you can buy today just off the shelf. Now, the mean time to failure drops to 17 years, but I would position that in about 5 to 8 years, I want a new computer anyways. So if it fails at 17 years, it's not going to hurt me. But by doing this, I've allowed myself to use simpler devices, less costly devices. I may have to use more of them, but the cost per device drops way faster than the cost of 4 devices would add up. And so what we end up with is a more efficient solution that gives us this 5 nines of reliability, which is economically advantageous. And here's the 2 charts put together, the mean time to failure and the system reliability. You can kind of see what happens. At some point, you don't want to lower your mean time to failure too far, but through the calculations, in the 4, 5, 6, we're still doing pretty good. And the idea here is that we're able to buy devices that cost a lot less. A Raspberry Pi costs a lot less than a server class system. And buying 4 Raspberry Pis, I don't know what the price has gone back to, but at one point we did use some, and they were 30, 40 bucks a piece. So for $150, I basically could replicate systems that cost in the tens of thousands of dollars. Go back to some edge platform quality attributes we're interested in. So right now, we have a hardware interchangeability and configuration reliability, based on the current proprietary capabilities. We can do simple N+1 redundancy. The proprietary hardware limits our ability to do any kind of interoperability, interchangeability. You can't go buy a new computer because the old, the replacement computer has to plug into the same connector as the old one. And a new computer wouldn't do that because the proprietariness. We don't do a lot of upgrades for these very reasons. We get very static in our functionality and our capability. The security, we're stuck in a world where we're using a lot of baling wire and band-aids and duct tape for our security, which is not a great place to be. And then, of course, when you're locked in and you only have one choice, the economics don't always work out in your favor as an end user. So with InterEdge, we said, hey, we could get some interchangeability choices here. We get more choice. We can start upgrading our equipment. We can replace one brand with another with maybe extra better features. We can be cost competitive because we introduce competition in the marketplace, and these are all good. And the other direction we want to go is to get more reliability. So we start looking at this N+X active redundancy, which we've been talking about a little bit here. You can decide how much reliability you want. If you want more reliability, you add more nodes or you increase the availability of the individual components you buy. You can reconfigure. If you change what you're doing and you decide you want to change the reliability, you can add more devices or change them to something more available, and that's very dynamic. Obviously, with the mean time to failure change, very possibly you will increase your hardware maintenance. But again, we're talking about replacing computers that cost tens of thousands of dollars with computers that might cost hundreds of dollars. And so while you may do more hands-on activity, hopefully the goal here is the total cost is actually less, more efficient. All right. So our goal is to move in this upper quadrant where we get both interchangeability and higher configurable reliability and allow us to achieve the same reliability we get today at a lower cost and more effectively. So how do we do this? So obviously to do more interchangeability, our solution has to be capable of adapting to whatever CPU architecture you might have. It might be Intel-based, it may be ARM-based, it may be MIPS-based or RISC-V based or whatever the computer chips that might be available. The devices should not have to know about each other. So there's no interrelationship. They should be independent and capable. The new hardware should also support modern applications, and that is one of the problems we do have with the legacy hardware is the modern applications don't always run on it. The computers are either too small, not enough memory, or maybe even not a more modern version. Same thing happens with the redundancy piece. We realized that publish subscribe was the answer. We did not want to have a broker in the middle because it creates a reliability issue you have to address, because if your broker goes down, your communication goes down. So brokerless would be great. We felt like this reliability, if it was managed in the intermediate, that messaging layer, that was more valuable than it being trying to managed in hardware or in application software specifically. So the communication manages this. And then of course, when you bring a new device online, well, how long does it take to sync up with its peers? And so the idea of support for late joiners. So to move to this upper quadrant, basically, we said we're going to try and figure this out. We're going to do some, I'll call it some pretty quick R&D testing, minimum viable product. We we brought in some really smart IT and OT people to work on this together, because it's not only just the software and the hardware, it's also the application that runs the process, or running a simulated process. Okay, so you can see the highlighted points here. You need in messaging, publish, subscribe, broker list would be great. Be able to configure the reliability in the messaging layer. Does that sound familiar? What we realized is we need something brokerless, publish, subscribe. We can manage the reliability via quality of service. DDS is the great answer. It's one of the few communication protocols that have these sets of features. It is the one that's easily approachable, and I think pretty easy to use and figure out how to make it work. All right, so let me tell you about what we did. So we set up a little rack of equipment, power supplies, communications, but got some processors. You can see some Raspberry Pis there, and a couple other devices that we have. And we set up a little system. And the idea was, let's use our control logic software and connect it together with DDS and see if we can use quality of service to figure this out. And some of the setup of this was, we needed a system that could run, but realize if you have multiple components together, what we wanted is a lack of divergence. Because if you start calculating and they all drift away from each other, it's not going to be as useful. The idea of using multiple components that can run sort of in a synchronized manner. And then one of the key pieces here is we didn't want to have synchronization be an objective function. We wanted it to just happen. It goes back to that statement about they don't need to know the others exist. They work by themselves, but as a group, they stay together. We ran a number of tests. We ran through this thing through cycles on about a 5 millisecond basis for hours and hours, and we would measure the deviation between the various devices. And as you can see here, we could easily hit 1/100%. And in some cases, we were able to show we could get to a thousandths of a percent. And in my world, that is way more than accurate, because we have mechanical equipment that won't tolerate that sort of accuracy. Just because you can measure, it's not something you can control. And so we set up a system to do our testing, and I'll show you a little bit about how we did this. All right, so in the process control world, you take inputs, and we're going to use analog inputs, which are numbers, not ones and zeros, discrete. These are numbers, 27.2, 1000.7 kind of numbers. And we would do calculation on, if you want to control the temperature, just like your thermostat does in your house, or your cruise control does, you give it a set point. I want to go so fast, or I want the temperature to be a certain thing. And the system figures out, should it add heat or add cooling to keep you at that temperature. And so those are your inputs and your outputs. The input is the desired temperature, and the output would be the control you use to get the real value to that target. In my case, I'm going to tell you about, we have a couple sensors and their inputs. These are things like temperatures, levels, flows, pressures. There's a variety of these kinds of sensors, and we're going to use a valve to control it. And simplest would be, say, we want to control flow. But so you have inputs here, and we have a computer. And you say, all right, so I'm going to need some topics. I'm going to have an analog input topic and analog output topic. And of course, the analog input topic says, hey, compute, here's your values. Computer does its calculations and sends values through the AO topic to the output. Very classic publish, subscribe going here, but oh, we want another computer. So But this one's an ARM computer. So this is important. We're not tied to x86. We could use something else. Now, what we might do is give these a different weight in terms of the calculation. And so with this, we're going to also synchronize what the calculation result is. So this way they tell the world, here's what I calculated, and then they can synchronize on that. And of course, we add the second compute is now reading the topics for the AI and writing the topics to the AO. And if we keep going, we can add another computer. We can even add cloud infrastructure. You send the data wherever you need it, and it gets used. Now, I'm going to do this here. And you can see these have an ownership strength. Compute 1 is a 200. Compute 2 is at 180. Compute 3 is a 160. The cloud will leave at 99. And how we use this is we basically said, all right, when the AO topic receives these feedbacks, it uses the highest ownership strength. So the AO topic is going to take all 4 feedbacks from these computing environments, and it's going to say, I'm going to listen to compute 1 because it has the highest strength. And if compute 1 were to disappear, then I will use the next highest strength, which would be the 180. And it keeps going until you get to the cloud infrastructure model. So this is the idea that the output has to understand who to listen to. And quality of service using strength was one of the ways we could do this. And so this is how you can solve. What you do not want is all 4 computers telling the output to do 4 different things. And this is why you sort of want to have this. And we call it voting. And we actually did try some other voting methods in our testing. We did some Bayesian voting, and we did some data analytics, clustering types of things. It's really interesting in that kind of voting. You can, if you get the answer wrong too many times, we can actually vote you off the island, so you're not voting anymore. But the idea that the simplest was the strength model. And the idea is saying, well, if I add more devices, I just add them in at some strength that's unique and different, then they will enter into the equation wherever they need to be. If I add one in, it's a 250, it would outrank all these. If I add somebody in a 170, it's going to be between compute 2 and compute 3 in terms of order of precedence. Okay. So that's where we were trying to do this. So what did we learn? Well, it's definitely possible to use brokerless DDS to give us sub-second industrial control. We showed that we could stay the four processors running the same algorithm, doing the same calculation, could stay together. They did not drift. We mixed and matched hardware. We mixed and matched operating systems even. The hardware did not have to have any direct knowledge of each other. The middleware actually took care of all that between the publish and subscribe the topics as well as the synchronization topic. So the other nodes knew the one that was selected and what its value was. And the way process control is, it tends to calculate a delta from the last value. So if you know what the last value is, even if it wasn't your value, you could start with that last value, calculate your next value, and go back to voting on what the output ought to do. We validated some of the concepts in terms of reliability and fault recovery. We were able to bring devices back up, and they synchronized very, very quickly, as in less than 3 or 4 cycles. The transfer of control, if you will, to a different device is instantaneous, because the highest weight disappears, the next highest weight is there, and they're already voting. The data is just used instead. We were able to do this not only on control and outputs, we also were able to use it on the human machine interface. So the screen did the same thing, show me the value of the valve, the output of the valve, and it basically said, well, what were the values that were sent and which one was used is the most. And so this is part of, you get a lot of reliability here just by, I'll call it invisible failover versus active failover. In today's systems, we get a lot of, it has active failover. One-to-one redundancy has worked very well for many decades. The challenge we have today is that the complexity of the data set and the synchronization required, the overt synchronization that's done, it's not always complete by the time the failover happens, at which point it doesn't do a bumpless transfer, stateful transfer of control. And that's like if you were going down the highway and you had redundant cruise controls, one died and your car stopped and then had to restart instead of just keep on going where it was. We want it to keep on going. And so that was really what it was. It took us less than just a little over 2 weeks to do this test. We are simple end users, and we were able to do this. What we've done is, we put down our theories, we figured it out, we tested it to the best of our abilities, and we think we have some really useful capability using DDS, and we've begun to start telling others that these are the kind of high availability tools that we really, really want. And so, while I've given you a process control application here, the same would go for other types of parallel computing, parallel communications requirements that DDS with quality of service really does bring the features that are necessary for this in the pub sub type of model. All right. So our next steps, and we have been doing some of these, trying to figure out scale and how to deal with, is the complexity going to get to this point? We arrived at PubSub because we knew that client server type app middleware was not scalable at the largest scale, and control systems do have a large scale. We're not talking about just dozens of connections here. We're talking about hundreds, if not thousands. So the pub sub model is really the better answer. But the thing you want to know is, will it scale? Even if it's better, does it just scale to 1,000 or 10,000 or 50,000? Those are important things to know. At 50,000, I'm not worried. At 1,000, I'm thinking I could break that. But those are the kind of things we want to understand. Obviously, we did voting. We did not really tackle the topic of security, because you have all these pieces of data floating around. How do you do the authorization, authentication, validation? And these are important concepts. And then, of course, just dealing with the data and how do you bring this to the hardware platform? And then, of course, just understanding more of what we could do with PubSub. We believe that that's the future in the process control runtime execution world for communication, and we've been telling every vendor that will listen to us, these are the kinds of availability and reliability we want. We actually coined a term, we call it high availability, and high availability is redundancy on steroids, using software tricks and tools, and preferably let your middleware be the enabler for this. DDS with QoS is definitely a great solution. With that, I'm at the end of my presentation.
So the first one is, given the variety of protocols available for the IIoT and edge computing, what specific features of DDS make it particularly well suited for applications requiring high levels of fault tolerance? And how does it compare to other popular protocols like MQTT or OPCUA in this regard?
So the two standout pieces are not having a broker in having to be the traffic director, and the second is the quality of service functions. The real standout, the brokerless piece just gives you that a basic reliability. You don't have to figure out how to back up your broker, if you will. But the QoS is a function that many pieces, middleware software protocols don't have, and the variety of things that are available via the DDS, whether it be the data persistence, you can catch a new participant up, um, bring them, because there are calculations that take a lot of iterations to. The one we did is very simple, but there are some that take, have to go through the whole data set, at least, 100, 200 data values, um, in order to get to a point where you are on par with the peers. I think the QoS functions of weighting and some of the security functionalities that might be available there are really the difference. And when you look at things like MQTT or AMQP or any other pub subs, um, they don't have a QoS function like this. Their pub sub is the classic, you know, broadcast it and pitch it over the wall, and hopefully somebody gets it. In the process control world, sometimes you got to have confirmation. Did you get it? Did you get the right value? Are you listening to the right value from the right supplier of the data? These are the kind of things that are important. We came to the DDS conclusion based on when we wrote down what we wanted to happen. It's like, oh, this one does it. Check, check, check. Interesting. Let's try it.
Yes, absolutely. Okay, another question is, can you discuss some of the key challenges you faced when integrating DDS with existing edge computing architectures, particularly in terms of configurable fault tolerance? How did you address these challenges to ensure seamless operation and reliability?
So one of the, for all the great features of DDS, it's not as common of a software function that you can get in the automation world. So we had to sort of build our own. So it's good that we figured out how to do it and we could do it. What we really want is to buy products with it built in for us, that it's already been done by the software and the hardware makers have already put this together. I think that's really it. I'm an end user. I want to buy products. I want to use products. I don't want to build them. I don't want to program them. I want the vendors and people who have a true interest in taking this technology and solving the solutions. I'm more interested in using the solution to solve my business problem. And so I would say that's really what it is in the automation world, DDS is not as common. It is becoming more common. More vendors are paying attention. I'd like to think that through the efforts of the vendors who do DDS and the uses that are out there and publicized, as well as some of the things we've done and point out that there's this technology you ought to be looking at. I think that's really where the difficulty for us to do this was. We found actually that it was fairly straightforward to build it and set it up and to try it, which was one, a relief, and two, exciting.
We have one more question. It says the situation you described seems to be very hardware centric. At what point does your language change where you call the solution software defined control, where the hardware is a detail but not part of the value chain?
Excellent question. The whole goal behind the Open Process Automation Forum and the idea behind is about open architecture and truly software-defined architecture. And so the proprietary world we've lived in for decades, computing and automation came about in the 70s. In the late 70s, it became very purchasable and usable, and progressed through 80s and 90s. The thing was, it was built by vendors who built hardware, so a very hardware centric view. A lot of the solutions that we were all taught to do were very hardware centric first, software second. Using the tools like DDS and other software capabilities out there in the modern world, what we've realized is what we truly need is software-defined process control. the hardware is the platform. You need networks, you need, wires and connectors, and you need power. But the reality is, the benefit and the capability is really in the software. Um, there is a person who writes a lot of articles in the automation world, and he says software is going to eat the world. And I believe that's the case. Moving to things like DDS with its capabilities and using it as the middleware, where the middleware provides features and functionality, it's just not a conduit or a pathway, um, is an example of software as a service. The application does its piece, the middleware does its piece, the hardware has its place, but in the end, I want to forget about the hardware. I want to use this software, so I need some computing and some network. I want to communicate using the protocol of my choice with the features that I need, like DDS. And you just use the software, configure it. You set up your topics, your applications do their thing, and life is good. And this is where I'd say the modern world has moved to. Modern computing, modern software technology. It's about the software. It's not about the hardware. Um, and that's a tough message to give in a room full of hardware people, but we all know what's happened to computers and cell phones and other electronics. It's not it's the functionality and the software and the capability. It's not the device so much. Device has to be adequate. Quality has to be there.
Okay, well, with that, I think we're out of time. So I want to thank you all for joining us today and encourage you to continue watching for what we have in store for 2025 as we expand on over 20 years of the DDS standard. Once again, if you'd like to get involved with the DDS Foundation or have ideas you'd like to see in future webinars, we'd love your input. Visit our website, dds-foundation.org, and click on the Get Involved tab. Thank you, David, for a wonderful presentation, and have a wonderful day, everyone.